Okay, so when we're talking about acid strength or base strength, there's two ways you can really say that an acid is stronger. So the first method is you can just memorize pKa values. So remember, a lower pKa value means that an acid is stronger. Another method is you can kind of have a qualitative understanding, and that's what I'm going to go through right now. There's five rules that you can look at an acid and compare their conjugate bases to talk about how strong an acid is. Something that might be good to do rather than just memorizing a bunch of pKa values and understanding these steps that I'm going to go over, it could also be really helpful if you just memorize a few benchmark pKa values. So if you look at a molecule, you can say, okay, I kind of know if this is a really strong acid or it's weak. Just something to keep in mind, and you'll get familiar with it as you do more acids and base problems. So the key to qualitative comparison of acid strength and I guess base strength also, is to compare the stability of the conjugate base. So remember, the conjugate base is just an acid where you pluck off that most acidic hydrogen. And most of the times in a question, it will say which of these hydrogen, or which hydrogen is more acidic, or which proton is more acidic. Or if it says which molecule is more acidic, they'll typically be the proton that they want you to remove drawn in. So really, really important. So a stable base is weak. So an unstable base is strong. All right? So I'm talking about bases, I'm moving into acids. So if its conjugate base is strong, or I should say, if its conjugate base is stable, meaning it's a weak base, then the acid is strong. Conversely, if its conjugate base is unstable, meaning that it is a strong base, then the acid is weak. Okay? So I'll just go over this one more time. This is a really important rules. To understand how to do, or to be able to compare acid's strength or base strength qualitatively, you need to understand this. These are really a couple important sentences to really commit to memory. So a stable base is weak. Unstable base is strong. If you have a stable base, a stable conjugate base, you have a strong acid. If you have an unstable conjugate base, then you have a weak acid. So in short, the more stable that a base is, the stronger, so the more stable that a conjugate base is, the stronger the acid is. So I'll just write that down here. Stable base, stable conjugate base rather, and so that should make sense. So if you have an acid that is strong, that means the base is weak. If you have an acid that is weak, then the base is strong. And it just so happens that if a base is stable, that it's weak. So what we're going to be looking at are factors that make an acid, or that make a conjugate base more stable. So there's four, sort of five, but it's four main ones, and then the fifth one is kind of a bonus one. So we've got four factors. So we start by looking at the atom. So we're saying, where is the charge? And it's going to be a negative charge, So, we're comparing the location of the negative charge after the deprotonation. So we have atoms that are in the same period, and that's the same row of the periodic table. We're thinking electronegativity. Which I'll abbreviate EN. So, the charge on the more electronegative atom is more stable. So this should make sense, because if you have an atom that has a higher electronegativity, that means it can handle a negative charge better. So it can stabilize it better. If I'm saying something can handle a charge better, that means it can stabilize it better. So an example of this would be, if I were to compare these two molecules. So which one is more acidic? I'll deprotonate right here and right here. So I'm now looking at the conjugate base. Well, so which atom is more electronegative? Oxygen or carbon? Oxygen is more electronegative. It can stabilize that negative charge better. So this is the more stable conjugate base. Remember, more stable conjugate base is the weaker base, which means its acid is stronger. That means this is the stronger acid. Okay? Now, what if we had atoms that are in the same group? And by the way, the electronegativity trend is farther to the right. So, to the right and up on the periodic table. Fluorine is the most electronegative atom, just to keep that in mind. So, atoms in the same group, which is the same column, size is the major factor. Electronegativity no longer matters. We're concerned about size. And the charge on the larger atom is going to be more stable. So if we were to compare, let's say we've got water and this guy over here, which one is more acidic? Deprotonate. Well, sulfur is going to be lower on the periodic table, because remember, size increases down the group. Sulfur is larger. It can stabilize that negative charge better. So this is the more stable conjugate base. It is the weaker conjugate base, which means that this is the stronger acid. All right? So that's kind of the game that we play as we go through all these patterns. So, our second factor is resonance. So remember what I said when I recorded that video about resonance. Resonance is a stabilizing factor, and it's something that you're going to use as an argument all the time. Well, here's a prime example of that. Resonance is a stabilizing factor. So, if you can pick up a conjugate base that has that resonance, then it's going to be more stable than the conjugate base without resonance. So an example of this. So as always, start by deprotonating. So, well, does this have any resonance? No. Here we do. We have an allylic negative charge. We have this negative charge in the allylic position. So I'm just going to move those electrons. So this guy is more stable because he has the resonance. So, more stable conjugate base, weaker base, stronger acid. Okay? The third factor, induction. So, you're going to, I guess I should take a step back and say these 4 factors you should examine in this order. So first you look at the atom, and if it's the same atom because there's no difference in the electronegativity or the size, then you move on to resonance. As you see, this was the case because we had 2 oxygen. We had oxygen molecules both bearing a negative charge, so there's no difference in the atom. So then we go on and we see resonance. Well, if you've gone through, well, they're both the same atom, they both have the same number of resonance structures, then you move on to the next thing, which would be induction. So you're going to look at the other atoms in the compound. And see if they are withdrawing electron density. If you have electronegative atoms that are withdrawing electron density, imagine that as them kind of pulling that negative charge towards them. They're kind of spreading it out. Instead of that negative charge just being concentrated on one atom, it's being kind of drawn away from it. And that's going to stabilize that negative charge, and hence stabilize our conjugate base. So, well, what do we have here? We've got, let me move this. We've got so what's over here? Let me draw the conjugate bases first. Okay, so here we've just got hydrogens, not very electronegative, and they're not even more electronegative than oxygen, so they're not really going to be doing anything. Well, here we've got chlorine, fairly electronegative, because remember the electronegativity trend to the right and up. So these chlorines are fairly electronegative. So these are going to withdraw electron density. You can represent that with a dipole moment like that. So that's going to act as a stabilizing factor. Notice how both of these molecules would both have one resonance structure, which is why we're moving on to the induction. So this has the inductive effect. It's withdrawing electron density, helping to spread out this negative charge, hence stabilizing the molecule. So this is going to be more stable. Therefore, so that's the weaker conjugate base, so its acid is going to be stronger. Okay, and I'm going to erase over here. I'll erase this part here. And I will draw our 4th part. So the fourth factor, if those other 3 have failed to show any difference, then you're going to look at orbitals, or hybridization. So let's see. So you look at the hybridization of the deprotonated atoms. So the stability goes SP is more stable than SP2, is going to be more stable than SP3. And the way I think of this, like especially, because most of the time this happens, it will be with carbons, so you can kind of think triple bond, double bond, single bond, just as kind of a general rule. So, an example of this. So I'm showing you this molecule and I say, well, which hydrogen is more acidic? Nothing else is going to work, once we deprotonate, so I'll go ahead and deprotonate. I'm just going to erase these hydrogens. Well, here we have an sp2 hybridized, and over here we have an sp hybridized orbital. Sp is going to be more stable. So that's the weaker base, more acidic. So the proton in this position is the more acidic one. Okay? And then the bonus effect, this really, I don't know if this would really come up on an exam or something, but just in case it did, and just to have in mind, solvation effects. So these only account for very, very minor, these account for like super, super minor differences in pKa's. So explains very small differences. And what this is saying basically is that smaller molecules are better able to solvate, kind of dissociate into solution. So they're going to be more stabilized than those larger molecules that are kind of bulky and sterically hindered. So they're going to be more stable. So it just says, so more stable. But again, this is not, the reason why I say this is kind of a bonus one is because this really, it's not a huge factor. It's not like you're going to see a difference of, 10 pKa's. It's like the example I have here. So you can see if I'm saying which one of these is more acidic, you might go through and say, well, I'll compare the conjugate bases. This OO, so same atom, no resonance, no inductive effects, because these inductive effects from CH3 is nothing. The hybridization doesn't play a role. So you might say, well, what's the difference? Well, it's the solvation effects. This guy has a pKa of about 16, and this guy's pKa is about 18. So, not a very large difference, but because it's smaller, interacts more with solvent, more stable. So that's going to make it more acidic. All right, so, and again, so this is, I was really talking about acids by comparing the conjugate bases, but if the question was which base is more stable, which base is stronger, well, it's the same thing. You just, whichever base is more stable, because remember stable bases are weak, well, the more stable base is the weaker one. And the less stable base is the stronger one, so stronger base, etc. So it's just kind of the reverse process, but most of the times you'll be asked to compare acidities. All right, and the key, definitely resonance is the one. This is the factor that's going to show up most commonly, so make sure that you're really good at recognizing those resonance structures and drawing them. So, all right, thanks guys.